Hello explorers and welcome to another video. Today we are doing the Advent of Code puzzle. The Git repository is linked in the description below, and if you want to see all of my trials and tribulations, you can see the full recording as a member of this channel. Day 10, let's see here. Day 10, Cathode Ray Tube. You avoid the ropes, plunge into the river and swim to shore. Okay. The elves yell something about backing up with them upriver, but the river is too loud to tell exactly what they are saying. They finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritized getting the communication systems on your handheld device working. You pull it out of your pack, but the amount of water slowly draining from the big crack in its screen tells you it probably won't be much immediate use. Unless, that is, that you can design a replacement for the device video system. It seems to be some kind of cathode ray tube screen, simple CPU that are both driven by a precise clock circuit. The clock circuit ticks at a constant rate, and each tick is called a cycle. Starting by figuring out the signal being sent by the CPU. The CPU has a single register, X, which starts with the value 1. It supports only 2 instructions. Add X and then V takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. It can be negative, okay? Noop takes 1 cycle to complete. It has no other effect. The CPU uses these instructions in a program, your puzzle input, to somehow tell the screen what to draw. Consider the following small program. Noop, add 3, x minus 5. Okay. Execution of this program proceeds as follows. The start of the first cycle, the Noop instruction begins execution. During the first cycle, X is 1. After the first cycle, the Noop instruction finishes execution, doing nothing. At the start of the second cycle, the add 3 instruction begins execution. During the second cycle, X is still 1. During the third cycle, X is still 1. After the third cycle, during the third cycle, X is still 1. After the third cycle, the add 3 instruction finishes execution, setting the X to 4. At the start of the fourth cycle, the add 5 instruction begins execution. During the fourth cycle, X is still 4. During the fifth cycle, X is still 4. After the fifth cycle, the add X minus 5 instruction finishes execution, setting X to minus 1. Maybe you can learn something by looking at the value of X registered through the execution. For now, consider the signal strength, the cycle number multiplied by the value of X register. Okay. During the 20th cycle, during the 20th cycle and every 40 cycles after that, that is during the 20th, 60th, 100th, to 140th, and so on. What the cycle number multiplied by the value of the X register. Okay, during the 20th cycle and every 40 cycles after that. Okay, for example, this larger program, so a bunch of instructions here. The interesting signal strength can be determined as follows. During the 20th cycle, the register X has the value 21, so the signal strength is 20 times 21. Okay. The sum of these signal strengths is 13,140. Find the signal strengths during the what is the sum of these 6 signal strengths? Okay. So just at these specific points, nothing else. So that's interesting. And during at the first cycle, loop instruction begins execution. During the first cycle, X is 1. After the first cycle, loop instruction finishes execution, doing nothing. So it's after the finished of each instruction, it actually does something. So we need to figure out what happens first, then after that instruction, we do the actual execution. That is interesting. So we have a bunch of numbers here. So now we need to run this program and get, let's go for the 20th cycle first. So we need to have a cycle counter that starts at 0. And then we will read each line. If line is equals loop, then we'll do something. And if line starts with add X, then we'll do something. So here we have the loop. We will check the cycle counter. If cycle counter is then we will $20, 60, 100, 140, 180, 220. And then we will have stops contains cycle counter. So if that is the case, then we will take the let's see here, long value equal to 0. Value is increased by the cycle counter. Let's say sum here. Times current value. So we will have a long with the current value as well. And this starts at 1. And this is the same for both of these. So first we check the cycle counter if there is anything. So here we will just take the cycle counter and increase it. So that is the end of that operation. And here we will take the cycle counter and increase it by 2. And here we also need to take line and split it by space and get the second value integer parse int of the first value. That's the second value. And then we will take current value and increase that with that value. So let's see what we get here if we run this. Run in debugging. We have a cycle counter of 100. So that's no good, because we should be able to stop at each of them. So the loop operation is fine, but here we should first try that then increase, and then try this again, increase, try it again, and then do the actual counting. And then we need a bunch of these stop points. So first cycle count, and the current value is 21. That is correct. So it seems like we figured that one out. And let's go for the next one, 60. Then the current value is 19. That is correct. Current value is 18 at 100. That is correct. 21, correct. 16, correct. 18, not 19. So if we try to change it up so we have the cycle counter first, what change does that bring? So I want to have this list here on this side. There we go. So the first should be 21, that's correct. 19, 18, 21, 16, 18. Okay, so that was the correct, and then we get the correct value. So you just needed to change when we actually counted the cycle counter up. Yes. So let's do like this. We go up top, and we switch out what we actually are running. Run the real example here and see what we end up. Then we get the value of 14,540. Let's go back here and put that in and see. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So let's continue with part 2. It seems like X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide, and X register sets the horizontal position of the middle of the sprite. In this system, there is no such thing as a vertical position. If the sprite's horizontal position puts its pixels where the CRT is currently drawing, then those pixels will be drawn. Okay? You can count the pixels on the CRT, 40 wide and 6 high. The CRT draws on top row of pixels left to right, then the row below that, and so on. The leftmost pixel in each row is position X, and the rightmost pixel is 39. Okay, like the CPU tried closely to clock circuit, is tied closer to the clock circuit. CRT draws a single pixel during each cycle, representing each pixel of the screen as a hash sign. Here are the cycles during which the first and last pixel of each rows are drawn. Okay. So this is the first 40 cycles and so on. So by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant each pixel is drawn, if the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn. The screen produces a lit pixel with a hash sign, otherwise the screen leaves a dark pixel, a dot. The first few pixels from the large example above drawn as follows. Sprite position. Begin executing add x15, draws at pixel position 0, current row, okay? Sprite Position. During CRT draws pixel position 1, finish executing, add 15, register X is now 16. Sprite position there, okay. Begin execution, minus 11, draws pixel in position 2, current row. CRT draws a pixel at position 3. And finishes executing add X, okay. The following program completion, the CR2 have the following image, okay. So need to figure out what they're doing here. So, by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible, the instant pixel is drawn, if the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn. The screen, the first few pixels from the larger example above are drawn as follows. Sprite position. So the sprite position is 3. Okay, now I'm understanding. So we have 3 sprite at sprite position 1. And then the sprite will move around here. And then during each cycle, we will need to figure out if the current block of the sprite is... This is interesting. So it moves around and then... Yes. So I get it. So... at each cycle, draw cycle, like that, and then we will have draw cycle, draw cycle. So that's when we actually draw. And then we need to have this current value, the cycle counter and the current value needs to be outside of so there is a cycle counter. So these two needs to be here. I need to be public, private can be also static. So we have them available to the program. So that was an alarm, but I don't have the on-call duty at the moment, so I don't need to handle that. And it will probably go off the next hour as well, because it have been unhandled. We have probably not been able to reach out to the newspaper at the moment. So let's see, we will need to draw a cycle. And we draw a bunch of cycles, but if the cycle is, let's see here, where did it go here? Cycle 1 to 40, so it draws the different cycles here, 1 to 40. So each 40th cycle, we need to, after that, we need to do a new line. Cycle counter equals cycle counter split by 40 equals 0. And then we'll do a system out print line. So a new line after that. And here we want to look at the current position of our sprite. And the sprite position is the 3 ones after 1. Yeah, we actually need to have the cycle counter here. Int current position is that, and if current position is equals to 0, then we will have the current value. If the current value is too far away from current position, so the current value, if the current position is less than the current value, or current position is larger than current value plus 3, then we will print out a dot, else we will print out the hash sign. So what does that yield? What's going on? Why do we have an extra print? Oh, do not do a print line, of course. So maybe we only do like that. We have a smaller range. That is not correct either. Let's see if we can tune our thing so it gets exactly the same. Now it's looking better. So we have the same up there. We have the same up there. Oh, we actually have 6. So close, so close. But the only thing we are missing is 1 at 1 position. It's super close. So maybe we can see the full picture now if we are a little crafty. Let's try it. We are very close to the right solution here. So E, H, Z, F, Z, H, E, H, Z, F, Z, H, Z, Z. So let's see if that is the correct response. So what is the 8 capital letters? So do I have 8 capital letters? I do. So let's see if that's correct. Yes! You get a gold star. I get a gold star. Everybody gets a gold star. So in this specific example, we are very close to the right solution, but not really there. But it didn't matter for this specific example. So let me show you what I mean here. So here we have what I actually was looking at. So this is the 2 pictures. This is the picture that they want us to draw. And this is what we draw. And you see here that we have an error down here. This one should have been drawn, and we don't. But it's so close that the actual output that we get is still readable, which is just fine for this example. So we get the right letters and we can complete the actual puzzle for the day. So what did we do? We had a bunch of these values up here. First off, we had a bunch of stops for the first puzzle, just to see where we should count things. We had a summarization thing, a cycle counter, so we knew which cycle we were on, and the current value that started at 1. The first thing that happens in each round here is that we add to the calculation of the circle counter. So if we are at circle 0, we go up to 1 for the first loop here, for instance. And then if we want to do anything else there, we can, for instance, here, or sum if the cycle counter is within these stops, so we can actually do the summation. But we also want to draw the specific cycles. We have a draw function that runs for each cycle in the sequence. And if we want to add a value, so it starts with add x, then we will do 2 cycle rounds first with drawing, just to get everything out of our buffer. And then down here we will change the actual value. So we split it up and take the second value of the string and add that to our current value. And it could be either a plus value or a minus value, so that's something to keep in mind as well. And then we print out the sum down here. The cycle function is pretty simple. We have this cycle counter. Ours starts at 0, but we want to mod it with 40. So we want the right cycle counter so we can actually have the right draw position, but we want to start at 0. So we add 1 to our cycle counter. We get the current position. We check that the current position is smaller than the values that we want to check within. So +1 to +3. And if it's either smaller or larger than the actual drawing sprite, then we will output a dot. But if it's within the drawing sprite, we will draw a hash mark. And then if we are at a new line, we are at current position of 1, then we will do a print line down here. So I hope that you found this interesting. I hope that you learned something today. If you like this video, give it a like, share it with your friends and colleagues. And if you have any comments or suggestions, leave them down in the comment section down below. If you have any code that you want me to check out, leave it down there as well. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.